Hi everyone, welcome to another hands-on session. In this hands-on session, we're going to work on the post process, and also we're going to plot the results that we got from the post process function. Now, in this session, I'm not going to write the code along with you because there's a lot of equations that we need to copy from the stiffness function. So I assumed that it would be easier for me and for you as well to watch me explain the code. But of course, you have to write the code for yourselves as well when you're watching me explaining the stuff. So you can pause the video, write the code into your file, and then continue watching the video when you're done. All right. So last time, if you remember, we completed the process and pre-process sections of the code. And then we got the extended node list, which contains the information regarding the coordinates of the nodes, the displacements and the forces. And then using these displacements and forces, we're going to calculate the strain, stress values for the nodes after they are deformed. So that's what we're trying to get in this session. To do this, I'm going to define a function post-process, which takes the parameters NL and EL, and also extended node list. I'm going to use the displacements in this extended node list to calculate the stress and strain. And in return, I'm going to get the stress values in 4 directions: XX, XY, YX, and YY. The same goes for the strain values. And finally, I'm going to get the values for the displacements in the X direction and Y direction, and the final coordinates of the nodes when they are deformed. So let's go to this Py file, which is named postprocess.py, and define the function postprocess, which takes the parameters NL, EL, and extended node list as I've stated before. And then don't forget to import NumPy and math as well, as you can see here. Now, as always, we're going to start with defining the problem dimension, the number of elements and nodes per element, as you know from the previous videos, the sizes, so you know about these. And I'm also going to define a scale to magnify the deflection. If you remember from the one-dimensional analysis, we had this exaggeration bar at the bottom to exaggerate the results. So I'm going to multiply the displacements with this value to exaggerate the plot. And below this, I will have another function, which is element post-process. And this is going to get NL, EL, and ENL as the parameters. So you can think of this as element stiffness function in the previous video when we calculated the stiffness. And then I'm going to get the results from this function and then pass it to this function to organize them in a nice way so that we can plot them later on. So let's go to this function below and see what we have. So we have the element post process and we have the parameters as well. So inside this function, what I'm trying to get is the displacements, stresses, and strains. So as you can see here, we have displacement, stress, and strain as the output of this function. So let's talk about these matrices here. But first, as before, we define the problem dimension, number of elements, and nodes per element. And then we also need to define the Gauss points because the Gauss per element is not directly passed to this function. So for D2TR3N, 3-noded triangular elements, the Gauss point per element is 1, and for D2 QU4N, the Gauss per element is 4, because we have four Gauss points, as you can see in this figure. So 1, 2, 3, 4 Gauss points, and then in this one we only have 1. But for the other element types, which you're gonna code by yourselves, D2 QU8N 9N, and then for D2TR 6N, you may need to modify that section. So for example, if I remember correctly, for the 8 and 9 noded versions of this quadrilateral element, I think we use 9 Gauss points, as far as I remember. So you may need to add additional if blocks in here to compensate for those element types as well. Now here, I'm going to initialize my matrices, which is going to be my output, as full of zeros, and then I'm going to fill the slots of this matrix as we go on with the code. So let's first look at the displacements. The size of this will be number of elements times nodes per element times problem dimension times 1. So let me just explain why we have these sizes for this matrix. So number of elements specifies the element I'm looking at. So I'm going to go over a for loop to go through the elements. So that's why we have number of elements. Second, we have nodes per element, which specifies the node on the element I'm looking at. So I'm going to go through each node for each element. So let's assume that we're looking at element number 1 or element number 19, let's say, a random element from the list. So this is going to be element number 19. And then we have 4 nodes attached to this element. And then I'm going to go through these nodes in a for loop. And then finally, we have the problem dimension assigned here. The reason for this is because every node on this element has 2 directions as that displacement can happen. So this node can move in the x and y direction. This can also move in the x and y direction, and this one as well. So that's why we have this problem dimension assigned here. So for each element and for each node in these elements, I'm going to look at each direction for each node. So that's the logic behind the size of this matrix. Stress and strain sizes differ from the displacements because instead of calculating the stress and strain values on these nodes, we calculate them on these Gauss points. And each Gauss point has 2 degrees of freedom, which gives us a matrix of, for example, for stress matrices, we have XX, XY, YX, and YY directions for the stress and strain values. So that's the main difference between the displacement matrices and the stress and strain matrices. So when we look at the sizing, again, we will go through each element for both stress and strain. And for each element, instead of looking at the nodes, I'm going to look at the Gauss per element. So I'm going to go through each Gauss point assigned in this element. In this case, so if you look at this element type, the number of Gauss points is equal to the number of nodes per element. But this might change, as I have stated before. You may want to add additional if blocks to your code to compensate for the other element types where you might have 9 Gauss points, for example. So that's why we have this parameter here, the sizing. And then as I've stated before, we have problem dimension and problem dimension. So instead of only having x and y directions for Gauss points, we have xx, xy, yx, and yy directions for the stress and strain values. So don't forget about this. And if you're confused about why this one is here, the reason for that is because it's easier to understand the logic. So I'm simply making this matrix similar to this matrix. So it's just a notation and it's not important. If you got these parts about the sizing, the rest is pretty much easy. Now let's continue with the for loops. And by the way, I added some hints on the screen, and you might want to read these if you're stuck or if you don't understand what I'm saying. These texts explain the material a little bit, let's say, more clear. So before moving on to the for loop, I also want to mention one thing. So we calculate the displacements on the nodes, and then we're going to map those values onto these nodes as well. But for stress and strain values, they are calculated on the Gauss points, as you can see here. But because of the shortcomings of Python and MATLAB, we will map these values onto these nodes as well. So this is sort of like cheating to plot the results. So that's why you might see these, sharp color changes between the elements. Normally, if we were to plot on the Gauss points, so let's think about Paraview. I think you've seen Paraview in class. Professor Javili might have shown you about Paraview. So in Paraview, you can plot the results on the Gauss points instead of the nodes, and you won't have these sharp transitions between the elements. But in this case, since we map the results onto these nodes, we will have, this little transition, and this is why the plot is not smooth. So this is the plot for stress XX. So if you look at the displacement X plot, you can see that the plot is very smooth and we don't have those sharp color transitions. The reason for this is because, as I've stated before, we calculate the color values for the displacements on the nodes, and we also map them on the nodes. So that's why we don't have that, sharp transition between the elements. So let's continue with the for loop now. The following for loops and the rest of the code is 70% copied from the stiffness function. So if you go to the stiffness function that we've written before in the previous video, so as you can see here, these for loops look very similar to these for loops. So as you can see here, we have 4 directions, but this time it's going to be for sigma. We again calculate the Jacobian and stuff. So I'm going to explain these step by step, but just know that you can just copy from this element stiffness function that we've written before and then modify it in such a way that it's compatible with the post-process function. So we will write a for loop for the number of elements so that we can go over the elements. So we will start by calculating the displacement for each node on each element. And we're going to proceed to the strain values. And then using the strain values, we're going to calculate the stress values. So the way we calculate the strain and stress is as follows. So to calculate the strain, we will have to use this equation here. So 1/2 gradient of u plus gradient transpose of u. So you may ask, what is u then? U is the displacement regarding each node on each element. So we have these corner nodes, right? And then each node has their own displacements. So if I know the displacements on the corner nodes, I can distribute the color throughout the whole mesh. So that's why we get the corner displacements, and then I'm gonna distribute the displacement using the shape functions, and then we're gonna get this nice color scheme, let's say. So this is the equation that we're gonna start with, and then we have these following equations. So as I've said before, this represents the displacements of the corner nodes, and then this will be equal to the shape function times the displacement of the node. So this is a numerical number which corresponds to one of the displacements of the nodes. And then if you take the gradient of it, this will be equal to the gradient of the shape function dyadic ui. So since ui is a number, we don't say plus ni dyadic ui, a gradient ui, next to it, since the gradient of ui will be equal to 0. So this is the gradient of this u. And then let me talk about this operator as well, if you see it for the first time. So this is also referred as a tensor product, as far as I know, but let's call that dyadic to differ from the other multiplication product. So the logic behind this dyadic operator is as follows. Assume that we have two row vectors, A is equal to A1 and A2, and then B is equal to B1 and B2. Both are 1 times 2, the size. And then what this operator does is that it takes these two matrices, it takes the transpose of this first matrix, and then it takes the second matrix as it is, and then multiplies them, which gives us a 2x2 matrix. So that's what this operator does. We also have this property below for this operator, dyadic, which is A dyadic B transpose will be equal to B dyadic A. And we're going to use this property above when we need to take the transpose of this U, as you can see. So that's the calculation process for strain. So let's proceed with that. So let's first go over the elements. As I've said before, I take the mini node list, as in the stiffness code, from the element list. So this will contain the node numbers for a specific element as I go over the for loop. So for a four-noded quadrilateral element, this may contain, let's say, 1 to 8 and 7. And then I'm going to assign the displacement to the corresponding nodes. So I'm going to go over the elements, the nodes per element, and then I also need to go over the directions, since we have x and y displacements. And then for each element, if you remember the size, for each element, E, which represents the element number, I'm going to look for a specific node. So nodes per element, nodes per element, nodes per element. And for a specific direction, which could be X or Y, so J goes from, 1 to problem dimension, and the size was also problem dimension. And we only had one column in the fourth dimension. So this is going to be equal to the mini node list that we created, which has the node numbers inside it, I'm going to subtract 1 to get the index for Python. So if it was 1, 2, 8, 7, it's going to be 0, 1, 7, and 6. So this defines the row for the extended node list. And then the displacements for each node are located at 4 times PD plus J minus 1th column. You know this from 1D analysis. So if you look at the extended node list, as you can see that we have the displacement for each node here. And then these are the forces, by the way. So I'm going to use these displacements to assign these displacements onto this matrix that we created before, or initialized before, let's say. So that's the process behind these for loops. Then we also need to specify the corners of the elements. So this is exactly the same as in the stiffness function. So as you can see, we have the corner nodes of the elements. So this is exactly the same. So I'm not going to explain it again, but this is the corner nodes. And then I'm also going to specify the displacement for these corners. And I'm going to use this for the strain. So this U is this U that you see here in the PDF file. So you may ask, why do we assign the displacements again since we did this in here? But the difference between these two is that I will update the U value as I go over the for loop for each element, and then this displacement matrix will be updated as I go over the elements. So this will be initialized as zeros over and over again, but this one already exists before the for loop. So that's why I have this U. And then the same logic applies here, but this time, since this is a 2x2 matrix, I have J and I values here. So J and I, which are problem dimension and nodes per element as well, as you can see here. And this is going to be equal to the displacements from the extended node list, just like in here. I also changed the row and column numbers. So I swapped these J's and I's compared to here to use them in these equations. Moving on, we have the core variable as in the stiffness function. The same thing. We take the transpose of the corner nodes to use them in the Jacobian and etc. Then we will go over the Gauss points to calculate each strain and stress value for each Gauss point. So these are the Gauss points, as you know, and then I'm going to calculate the strain and stress values for each Gauss point. So that's why I have this for loop. For each Gauss point, I'm going to initialize epsilon as np.0's PD. So it's going to be a 2x2 matrix because of this property you see here. So we have 2 degrees of freedom, which gives me a 2x2 matrix. So xx, xy, yx, and yy directions. Then I'm going to go over the nodes in the element. And this part is exactly the same as in the stiffness function. So this part here, but the only thing which is different compared to our function is the loop, and we just swap the order of these loops. So it's exactly the same. So don't forget to change this for loop to I in range instead of GP. So we swap the places of the for loops, as you can see here. And then this calculates the Jacobian, the gradients, the gradient of the shape functions. It gets the Cassie, eta, and alpha values from this Gauss point function, which is below here that we defined in the previous video. It also calculates the gradients, nats, from that function as well. It's below this file as well. It calculates the Jacobian, the gradients as well. And then finally, if you look at the stiffness code, we had this for loop to calculate the stiffness for each element. But this time, since we're not interested in the stiffness, but rather the strain values, we replace these four for loops in the stiffness line with this single line that allows us to calculate the strain. So this was the equation that we were going to use to calculate the strain for each Gauss point. So it's whatever value we had previously on that slot plus 1/2, which is this 1/2 you see here, multiplied by dyadic gradients U and U gradient. So before I move on to this part, let's consider looking at this dyadic function. So here we have this dyadic function defined, which takes two matrices. So these U and V's correspond to these A and B matrices you see here. So it takes two matrices, shapes them to row matrices. As you can see here, both should be row matrices. So I will reshape them to whatever the length they are to 1, which makes them row matrices. And then the problem dimension is equal to 2, as always. So as I've stated in the PDF file, you take the transpose of the one of the matrices and then multiply them. And then this will return the multiplication result. So if we go back to the strain calculation line, so dyadic gradient times the displacement, which is this variable right here, and this is going to be equal to gradient of ni dyadic ui. So that's why we have gradients of the shape function times ui plus this plus gradient transpose u. So inside this function, as you can see, the order is kind of weird, but this order compensates for this transpose. So you simply pass this u times gradient, and then it automatically takes the transpose. And this completes the strain calculation for a single element, for a single Gauss point, let's say. And that's it. Now, since we have the strain for a specific Gauss point, I can now calculate the stress using this equation right here. So again, we have directions. So we have ij directions for sigma, so xx, xy, yx, and yy. We also have this ijkl directions. So this was a, b, c, d in the stiffness calculation. And then finally, we also have the directions for the strain, which is xx, xy, yx, and yy. So this is the calculation process for the stress. First, I'm going to initialize the stress matrix as a 2x2 matrix, just like the strain matrix. And then the same logic as in the stiffness calculation applies here. So we had 4 directions for the constitutive function that we had before. So if you go back to the stiffness file, you can see that we have ACBD, but in this file we have ABCD. The order doesn't matter since these are just variables, but you just change the index according to the for loops. So in here it's sigma AB, but in the stiffness calculation it's AC. And obviously if I were to change this C with B, if I swap these two, I think these two lines would be exactly the same except for the sigma. But this is the way I wrote the code before, so it doesn't really matter. You can just play with the variables and name them whatever you want, but this is the way I named them. So sigma is going to be equal to the whatever value in that slot is there before plus the constitutive E, which is this one, times the epsilon. So this was ij, so in this case it's going to be AB. This was ijkl, abcd, and then finally this is kl, which is C and D. And then obviously we have these minus ones to compensate for the indices in Python. And that completes both the stress and strain calculations. Finally, after this for loop is over, I'm going to place these values of stress and strain onto this global stress and strain matrices, tensors, let's say. So we created these matrices before here, and we're going to find the corresponding slots for these stress and strain values and then place them accordingly. So in here, we go for 2 for loops in problem dimension. And then as you remember from before, we were going through the number of elements. So this is going to be E, which went from number of elements, and the size were number of elements as well. And then the Gauss point that we're interested in, so the size of the matrix was Gauss per element, so that's why we have this Gauss point here. And then finally, I'm going to have the problem dimension times problem dimension, like xx, xy, yx, and yy. So it's going to be A and B to compensate for that. And then this is going to be equal to epsilon AB and sigma AB, as you can see here. So A and B are x and y, and then these for loops ensure that we got the directions for xx, xy, yx, and yy. So that's the logic behind it. And then this pretty much completes this element post-process function. At the end, you can just return the displacement, stress, and strain as a tuple. And now I'm going to use this output in the post-process function. Now, all of these matrices, stress xx, xy, yx, yy, strain values, and displacement values, will have the size nodes per element times number of elements. So essentially, if you look at the form of these matrices, so for example, for D2QU4N, the 4-noded version of quadrilateral elements, we have 4 nodes, so 4 rows, as you can see here, which is the node per element. I will have the corresponding color values assigned as the stresses, strains, and displacements. So for example, for the first element, we have the color values as such, and for the second one as such, third one as such, so on and so forth. So element number 1, element number 2, 3, 4, 5, 6, 7, 8, 9, 10, and it goes on like that. The same goes for the stress matrices and displacement matrices as well. Nothing changes. Since we're going to plot the results onto the nodes instead of the Gauss points, the size of the displacement matrices and the strain and stress matrices are the same. And then I'm finally going to initialize the coordinates as well. We have 4 nodes and several hundreds of elements. So that's why the size is like this as well. And then I'm going to define an if block here. So if nodes per element is equal to 3 or 4, first I need to calculate the coordinates of the nodes after they are deformed. So x and y will be equal to the node number minus 1 to compensate for the indices in Python. So this determines the row numbers, and then this determines the x coordinates, plus I'm going to multiply it by the scale that I defined above. So you can change this to any value you want. So this value is going to change as the slider changes in the GUI, times the displacement from the extended node list. So 4 times PD brings me to the displacements in the x direction, and then I'm going to multiply it by the scale, and then add it to the initial node coordinate. So essentially, it's the exact same thing that we did in as in the one-dimensional analysis. I'm adding these x values to these values, and then that gives me the final coordinate of the node. The same goes for the y values as well. So I have these y values here, and then the y values, the displacement for the y direction is here. So that's what happens here. So that's what's happening here. And then I'm going to take the transpose of them to make them look prettier. Obviously, you don't have to take the transpose of them, but I would like to see the number of rows, the number of nodes per element as the number of rows, and the number of elements as the number of columns. So I would like the form to be like this. As I've said it before, I have 4 nodes per element, and I'm going to see the corresponding values in the columns. So it's just about the looks, but I suggest you to do the same. But you can play with this. It doesn't really matter. And then we can move on to the stress and strain values. As I've stated before, though every single matrix will be in the form of xx, xy, yx, and yy, and then I'm separating these values from this 2x2 matrix. So I copied this matrix to here as well, so that we can track the row and column numbers here. So for every value in the stress xx matrix, for every element and every Gauss point, if you remember, the size of this matrix was number of elements times Gauss per element times problem dimension times problem dimension. So for each element, inside these elements, for each Gauss point, this one, I will be looking at the first row and the first column to get the xx direction of the stresses. So this is the first row and first column of this 2x2 matrix. That's why we have this 0, 0 here. And then at the end, we have this transpose to match the sizes of these stress and strain matrices with these x and y coordinates. The same logic applies for the rest of the matrices. So let's look at xy values. So xy is in the first row and the second column. So that's why we have 0 as the row number and 1 as the column number. So the first row and second column. And then for yx, we have the second row and the first column, as you can see here. And then finally, we have second row and second column for the yy values, because yy values exist in the second row and second column. The same logic applies for the strain values as well. And then finally, we have displacement x and displacement y. So this time, if you remember from the element post-process function, the size of this was problem dimension times 1. So we only have x and y as a row vector, let's say. So that's why we have the x displacements and y displacements as the rows, and we have nothing as the columns, since we have only one column. And then I take the transpose for every single matrix, as you can see here, to match the sizes of the matrices with the x and y coordinates. And that completes the post-process function. At the end, I'm going to get the output of every single matrix that we created here. So stress xx, xy, yx, yy, strain values as well, the displacements, and then finally the coordinates of the nodes. Now, let's go back to the main file here. And since we have the information regarding the stress, strain values, and the coordinates of the nodes, the displacements as well, now we can proceed with the plotting. So the next section of the video is all about plotting the results that we got from the post-process function. But in Python, or in matplotlib specifically, it's very hard to plot these results without making some workaround around the functions. So this is my own solution for plotting these results, but you can come up with your own solutions, and you can even use another library if you'd like to, if you have the time to learn it. But this is the solution that I came up with. It takes a little bit more time compared to the MATLAB solution. So if you were to make your projects in MATLAB, your calculations may take less time to calculate, but this is the solution that I came up with, and we have to go with it for now. So my solution, in short, can be explained as such. I normalize the color values between 0 and 1, as you can see here. The reason for this is because I truncate the color map. So color map values vary from 0 to 1, and Python doesn't automatically normalize the values for you. So I have to normalize the values between 0 and 1, and to do this, I subtract the minimum value from the original array and then divide it by the difference of the maximum and minimum value of the matrix. The same goes for the displacements, the same process. So you can repeat this process for stress xy, yx, yy, strain xx, xy, yx, yy, displacement x and displacement y. But I'm only going to show these two plots in here, and that's going to be it. But you can literally just copy and paste these expressions and then change the variable names to match the matrix names, let's say. So after calculating the normalized versions of these matrices, so if you look at these normalized matrices, the values vary between 0 and 1 for the color values. Now, I will create a figure here, as you know from the one-dimensional analysis. I'm also going to name the figure as stress xx, and then I'm finally going to add an axis to this figure to plot my results. And this brings us to the for loop. So I'm going to explain what this truncate color map does, but let's first proceed with the for loop. So the way my solution does the following. It goes over each element. It takes the corner nodes of the element. So x will be x ith column. So if you go to the X matrix here, so all rows, so these 4 rows, and then the ith element. So each loop will take these values as the x and y values. And then I also get the color values from this normalized matrix as well. So I'm taking these values here, and each of these values correspond to x and y coordinates of a single node. So this corresponds to node, let's say node 1, this corresponds to node 2, 3, 4, and etc. So it goes on like that. So after I get the color values, the coordinates, and etc., I proceed with this truncate color map function. So this function You don't have to know this, by the way, you can just copy this, but just for the sake of explaining what's happening here, I can say that this function takes a certain area of a color map. So let's say we have this whole color scheme. So at the very left side, where can I show this? So imagine that I have a color bar, a color map here, and then the very left side is blue, and then the very right side is red, and then in the middle I have green, yellow, and etc. You know, all those colors in the jet color map, for example. And then each time I go over the for loop, I will get a certain part of the color map, and then I will assign the values using this color map. So I'm not getting the whole color map from red to blue, but let's say I'm only getting from yellow to green. So that's what this function does. So after you get the color values here, you can proceed with plotting. So I use the trip color function here. You can also use the tree contour f function method of the matplotlib, but I found this to be faster according to my results, but you can also try this. Maybe this will work with your code better. I'm not sure. Anyways, you plug the X, Y, and color values here, and then you also plug this color map here. And then finally, you apply a shading of go-route shading. So this smooths the graph, and instead of getting pixelated results, it just gives you a clear plot. And then this completes the color plots. And then finally, you see we have these black lines around each element. So these lines are called edge colors. And then in this final line, I simply pass the X and Y coordinates of each element. And then I set the color of the line to black. So if you remember this from CS115, so you can set the color of the line to black by writing this. And then I set the line width to 0.5 because I don't want them to be visible that much. And that completes the plot. So you may be asking, why do I have these t and p is equal to these plots, plot variables? Well, if you look at this section here, I explained it a little better in an organized way. So you can collect the lines and colors as variables to turn them on and off in your GUI later on. So in your projects, you have to include a feature where you should be able to change the color map. So for now, we have the jet color map, but then when I click on a button, I have to get, for example, magma color map. I also need the functionality to change, turn on and off these black lines around these plots so that I can see the plot more, let's say, clear. Okay. And so for these reasons, we have to assign variables to these functions. Now, so there's some examples that I wrote here. So I collected black lines, edge colors, as I've said before, in a list called plist, as you can see here. So I append the plist with p, the black lines, and I use this to display hide black lines in another function. So if I click on a button, it hides the black lines, and if I click again, it just turns them on and again. So that's why I collected these black lines in a variable called p. Another example here is I collected color maps for each element in a list called CMap list, which is this one. So I passed the color map that I truncated before to this list. And the reason for this is that I use this to redraw the plot. when exaggeration changes and when color map changes. So as you change the exaggeration value, you have to replot the results, but only the x and y coordinates. So you're going to use this C map, and then you're also going to use the coordinates, the new coordinates of the exaggerated plot to redraw the plot. And you can also use this variable when the color map changes. So let's say I wanted to see, instead of jet, I picked, magma as the color map. Then when I click on the magma color map, you will redraw the plot using these truncate color maps in x and y coordinates. So that's what this variable is for. I also collect the color values for each element in a trip list, which is this one, the trip color. So this is used to redraw the plot when the color map changes as well. So when I click on magma, the coordinate doesn't change, but the color map has to change. So I have to change the color of the trip color, and then the C map will be applied from this variable here that you collected in the C map list. And then finally, I collected the min and max values in the list. So when the color map changes, you may need to call this function again and maybe retruncate the color map to get the new plot. And that's pretty much why these variables exist in my code. So obviously, I don't expect you to get this in 3 minutes, but I can always help you with the plots or your code, projects, anything if you're stuck. So reach me out if you need support about these plotting things. And I assume that you definitely should contact me, because I don't think you can figure it out by yourselves. But obviously I can show the functionality of each button in my GUI. So I prefer, if you reach me out, I can just show it to you. But that's just something that you should keep in mind. You can always contact me. So the same steps go for the displacement X. I create a figure, title, get the axis, and plot the results. And that pretty much completes the post process. So if you run this, it takes a couple of seconds for it to calculate and then plot as well. So the calculation is done. Now it's plotting. So that's why I don't like matplotlib for finite element method. It takes a little bit more time to plot. As you can see, we have these plots. So this is the stress XX. And this is the displacement X plot. So if you realized, the transition between the elements are sharp here but smooth here. And as I've stated before, when we were talking about the post-process function, we assign the displacement values and also calculate the displacement values on the node. So that's why the values are exactly at where they should be. But in this plot, we calculate them on the Gauss points, but we plot them on the node numbers. So that's why we have this weird plot in here. So that's it. Let's proceed with the examples of some structures, and you will have some benchmarks to compare your results to mine. All right, so here we have the GUI for 2D FEM for the second project. So let's start from the very first part in pre-process. So first we can go through the inclusion shapes, which are circle, square, or rhombus. As you can see, when I click on them, the image changes as well. So we have these three types. And then we also have the dimensions and number of partitions. So A, B, C, D, E. As you can see from the picture, A is this side, B is this side, C is, if I'm not mistaken, it was P in our code, and then D was M, and then finally we have E, which would be R in this case. And then we also have the element type section. So we have 5 types, as you know from the previous videos. We have D2TR3N, 6N, D2QU4N, 8N, and 9N. So let's just keep it 3N for this time. And then we also have this checkbox, which decides if we have inclusion or not. So if this box is checked, we will have this void filled with extra nodes and elements. If this is not checked, this will be void, basically. So after defining these parameters, let's just click on Generate Mesh. As you can see, we have the mesh, depending on the parameters we defined before. I also added this extra feature. So if you click on this and generate again, you can see that we have this nice little animation, but you don't have to do it. This is something that I added just for fun. And then we also have this section which shows the number of nodes and elements in this mesh. You can also click on Reset Mesh to clear everything, including the analysis plots as well. So let's generate this again. And then we have these parameters right here. So for material properties, we have the matrix part and inclusion part. We have separate Young's modulus and Poisson's ratio values. So we have void. If we include the inclusion, this section affects the inclusion's parameters for E and Poisson's ratio. But if you don't have it, if this is void, whatever you make this section, it doesn't affect the results because we don't have an inclusion in the mesh. So you may prefer to make this disabled when there's no inclusion in the mesh, but I decided I'll keep that open. But it would be a nice addition to your projects if you keep this disabled when we don't have an inclusion. So keep that in mind. And then the next parameter, the next section we have in the process part is the deformation type. So we have extension, expansion, and shear, as we discussed in the second video or third, I'm not sure. So in one of the previous videos, we said we set the boundary conditions for extension, expansion, and shear. So those if blocks are determined in this section, depending on what the user picks from these radio buttons. And then we also have this deformation magnitude that we defined in that boundary condition video as well. So we have this as well. And then speaking of which, I also would like to mention that in that boundary conditions video, we wrote that code for only the case where A and B are 1. So if the user changes these two values, the code will still work for the values 1. So if you would like to implement this feature, you have to change that 1 with these A and B values. So getting the values from the entry boxes from here, and then changing the function parameters. So let's say if I change this to 2, you can see that the dimensions change. So the structure in the x direction became 2, the length of the structure. So let's just change this back to 1. So keep that in mind. And then finally, we have the run button. So here you can see that we have 2 analysis types, polygonal and shaded. You don't have to worry about this. I already showed you the analysis type as shaded, where we use the trip color function, tree p color, or tree f contour as well. You can use that as well. So this was just an experimental feature. You don't have to implement it. So you don't have to implement this section. Now, if we click on run, now you can see that we have this analysis. Since we don't have inclusion and also the number of elements and nodes are fairly low, it didn't take much time to calculate this plot, to draw this plot. So you can go through the different sections of stress, strain, and displacement. So this is xx values, this is xy, yx, which is the same as xy, and then we also have yy, and then finally we have the strain values. So you can go through them with the mouse wheel as well. And then we have displacement x and displacement y. So that's it. And then what else? We also should have a color bar next to it, I think, but I'm not sure if I implemented it, but I'll check that out. I'll see if it was necessary. So maybe it was, oh, this is because it's polygonal. So if we make this shaded, I think, yeah, now we have the color bar, yeah. So that was experimental. That's why the result was kind of off and we didn't have the color bar. So don't worry about this. So in the shaded part, we have the color bar, as you can see, the values. So I'm just going to go through the different sections of stress, strain, and displacement to give you some idea about the values you should have at the end of this project. So I'm slowly going through the values here so that you can compare them. You can just stop the video if you want to compare them. So let's just go through them nice and slow. And yeah, so that's it. Now, as we discussed before, the plot has solid color for each element because we have the element type as D2TR3N, which only has one Gauss point. So that's why we have a solid color in these sections. But in displacement X and displacement Y, we plot the displacements and also calculate the displacements on the nodes. So that's why we have this color distribution here. And then in the post-process part, you can see that we have these color map choices and then the scale. So let's just wait for it to update. So let's go, yeah. So you can go through the values. So if you remember from the first project, my GUI was able to update the plot simultaneously with the slider, but in this project, since the calculation takes much more time compared to the first project, I didn't want to make this update live because that would cause lag in the slider. So I can show this to you if you ask me during the projects. I can come and help you in some Zoom session so we can arrange that. Anyways, we also have the color maps here, so I click on them. It takes a while to change them. So that's one con of Python, or let's say Matplotlib. So we don't have a function to efficiently change the color map or redraw the plot. So this isn't something to worry about in your case, because I know it takes time to calculate. So don't worry about it if the program freezes for a couple of seconds, maybe 30 seconds, 40 seconds, and such. Anyways, we also have this tick, so you can just disable and enable the lines here. So let's just go to the displacement as well. So you can just disable and enable this. And then finally, we have this export all button, which exports the results in a file which has the format .vtk. And then in this way, I'm able to view the results in Paraview. This isn't something necessary to implement your projects, but as far as I know, if you implement this feature, it may grant you additional points in your projects. I'm not sure, but any feature that you add to your projects may grant you additional points, and this is one of them. So if you ask me about this in an email, we can arrange a Zoom meeting, and I can kind of show you how to do it. But obviously, I'm not going to do the whole thing. You have to do it by yourself. And so that's it for the buttons. Now, I will pass some structures on the screen to give you some ideas about the values you should have at the end of this project. So please pay attention to this bar in the following figures and compare your results with your own project. So let's just clear this structure, and then let's choose circle inclusion, and then D2Q4N, and then I'm going to change the dimensions to 5 this time. So let's just create this. Now we have this nice little structure. And I also would like to mention one thing about this. So circular inclusion. So as you can see, this section was void instead of, being full of elements. Now, the way you have to code this is that you have to combine the uniform mesh and then the mesh with the inclusion. So the thing inside, as you can see, we have these, 5 elements? Yeah. At the very middle, we have a square, which has 5 elements inside in each edge, let's say. So this is a uniform mesh, and then the mesh around it is not uniform. So the uniform code works at the very middle, the square part, and then you also have to find a pattern, a mathematical expression for the discretization of the inclusion part. So inside a circle, we have the square. That's the way you have to code it. Now, if we come to the square inclusion, this is the easiest to code. So we have this uniform mesh, and then you connect it to this section, the outside section. And then finally, we have the rhombus. So it should look like this. So let me just decrease the number of elements so that you can see it a little bit more clearly. So as you can see, we have this rhombus shape, and then we have 1, 2, 3 elements in that direction, and then this direction as well. And then in the middle, we have this square as the uniform mesh, just like before. So I'm just going to increase this to help you see it a little better. So let's just do that. Yeah. So this is what it should look like approximately. So we have the square, and then around the square we have the shapes to cover the inclusion. So you can just play around with this and code this. So I'm just going to go back to the circular inclusion and then increase this to 5. And then we also have to decrease the diameter. Yeah. So that's the mesh. We will apply extension. The parameters are right here. And then finally, I'm just going to press run. It may take some time to calculate, but I'm going to fast forward to the calculation. Yeah, it didn't take that much time because it's 5-5. So yeah. So these are the XX values here. I'm just gonna change the color map to jet to help you see it a little better. So it takes a while to change the color map. Yeah. Okay, so I'm gonna disable the edges so that you can see them easily, the distribution. So this is stress XX, XY, YX, YY. And then we have strain XX, XY, YX, and YY. And then finally we have the displacements, as you can see. Displacement X and displacement Y. So this is one structure that you can compare your results to. And then let's also talk about the square inclusion as well. So let's make this 550.3. And then the element type would be 8-noded version. Yeah. So let's do that. Oh, that's square. Yeah. Okay. So square D2QU 8N 55 0.3. So that's the structure we have. So let's apply expansion to this, let's say, and I'm going to change the plot to XX back again. So let's just run this. Again, it may take some time to calculate, but we have plenty of time. So I'm just going to fast forward if it takes much longer. But as you can see, the GUI freezes, and one way to prevent this is to, put a command in the command line like root.update or something like that. So it keeps the GUI updated. I can teach you to do that if you would like to ask me in an email. So we have XX, XY, YX, YY, strain X, XY, YX, YY, displacement X, and displacement Y. And that's it for that as well. Let's also apply a shear to, let's say, this element type. So let's make this 6-6, shear, generate mesh. Yeah, so I'm assuming this will take a little longer compared to the other meshes because we have more elements and nodes. So let's just click on run and then wait for it. So it will freeze for a moment and then we'll be back with the results. All right, it calculated. So I'm waiting for the plot to update. Yeah. So we have stress XX. So let me just disable the edges. Stress XX, XY, YX. It's still drawing the plots, so that's why we have this. It's not a bug. It's still calculating. So YX, YY, strain XX. It's still drawing. Yeah. So strain XX. So let me just wait for a little bit for the other plots to draw. So this is going to be strain XY. YX will be the same. And then we have YY. So let me just wait for it to update. Okay. So that's strain YY. And then we're also going to have the displacements. So displacement X. And then displacement Y. So yeah, that's it. So let me just go over them one more time. All right. So the important point here is to have the distribution correct. The values could be, 2 times of what I have here, depending on the boundary conditions you defined. So I'm assuming the other teaching assistant will have the boundary conditions defined for extension as, fixed from the left side and extended from the right side. In that case, since the displacement will be 0.1, the deformation magnitude will be only 0.1. So that program will probably give you the half of the values we have here for extension. But since I have defined them minus 0.1 to the left side and 0.1 to the right side, I'll have the double of the values compared to that video or the program. I'm not sure if this is true, but I'm just assuming. Anyways, so that's pretty much it. So we can do more benchmark tests if you would like to. You can just ask me in email. And I'm also thinking about showing this Paraview feature to you as well. So yeah, we're gonna talk about it. Anyways, so that's pretty much all of it. I hope you guys enjoyed. I hope you liked what I did in these videos. This is probably gonna be the last video, so that's why I'm making this speech. Anyway, then I wish you good luck in your projects, and then see you next time. Take care.